Hello everyone, Dr. Belmont here, and today we're going to continue the discussion of my Organic Chemistry 2 course with the topic of acetals and hemiacetals. So let's go and get our screen here. Let's open a new page, right? And what we're going to discuss today is the protection of carbonyl groups, right? The protection of carbonyl groups. Very well. So what is this, right? Well, actually, if you take my course of Advanced Organic Chemistry, you will see that constantly we will be using carbonyls for many things, right? And this is because, well, we already know that this carbon has a partial positive charge, and this oxygen has a partial negative, and this creates that the dipole moment will be pointing towards what? The oxygen. This gives the carbonyl groups a very specific reactivity, right? Because they are susceptible to what? To an attack towards of a nucleophile in which the electrons will move towards the oxygen. And then this opens, right, a collection of reactions that we can do with them. But sometimes, right, just because of the convenience of your reaction, because of the convenience of your synthesis, you do not want the nucleophile to attack, right, the carbonyl group. You need to sometimes we need to figure out a way in which a nucleophile will be present in the reaction, but you precisely do not want it, right, to attack the carbonyl group because it suits for our interests, right? So we need to do something. We need to transform this into something non-reactive. Non-reactive. Very well. So how are we going to do that? We need to figure out a way. Well, guess what? It is possible because what we're going to do is that we're going to protect the carbonyl group. Let's go to a different page. So imagine that I have, my pen. There you go, I have my pen. I have this, right? And it's going to be a ketone, any ketone, it doesn't matter, right? And I'm going to transform this into something quite different. Something like this, right? And as you can see, what we transform is an sp2 carbon, right, with an sp3 carbon. So the reactivity of this carbon has already been diminished dramatically, right? There's no way in which to an sp3, a nucleophile, like this one, can go and attack, right? Because it's already full of electrons, so there's no space for the electrons to be attached from with the nucleophile. But as you can see, this carbon, my pen, thank you, this carbon, it's attached to what? To two oxygens, which they are also pulling, right, a lot of electrical density. That particular case is going to allow us, right, at will, to return back to the ketone configuration whenever we want. So what we're doing here with these protecting groups, right, it's a convenient exchange, right, between two chemical, how can I say, structures that will help us or aid us in the reaction that we want to carry about. So let's go ahead, right, and first try to look how we're going to move from the sp2 to the sp3, from the ketone to the acetal. That's the name of this functional group. This is the acetal, right? And for example, if I have an aldehyde and I want also to do some interconventions with it, it's going to be something like this, very similar, right? But with a hydrogen, and this is called the hemiacetal. Very good. Acetal, only L. There you go. Okay, so let's turn the page and let's see how are we going to do it very well. So what I have is my pen. There you go. Is that I have my carbonyl group and I need two alcohols, right? And I can have two alcohols in the way of this structure, right? You can use for example, two methanols. If this wasn't a methanol and if this was another methanol, it would work very similar. But this is a very common one, right? And since the alcohols are attached, the yields are doing better. So we need two alcohols, okay? And also a little bit of acid as catalyst. Very well. And what we're going to do is that we're going to transform these two double bonds into something different. So what do you think is going to happen first? So I have a positive charge and I have available 2 electrons. So the first and most plausible thing that is going to happen, right? I'm going to erase this. I'm going to draw it here. I'm going to draw it here. There you go. Okay, so it doesn't get in our way, is that these 2 electrons will go and attack the positive charge of the proton. So what we will have is something like this. An oxygen that it is positive, and as we know, oxygen doesn't likes, right, to be positive. So what it means is that this positive charge is going to be more reactive. Why? Because the electron is even pulling the electrons more due to the positive charge, because it doesn't want to be positive. So now what's going to happen is that the electrons of the oxygen will attack, right, and push the electrons towards the oxygen that is positive. And what we will have is something very similar to this. We have the OH that was previously the double bond. Now I have the oxygen, right? That, as we know, is attached to the hydrogen, so it's going to be positive because it has the carbons, and another OH. Very well, so we have this. And again, what do we have? Another positive oxygen, and oxygen doesn't like to be positive. So within an intermolecular reaction, what is going to happen is that these electrons are going to pick up the proton from the oxygen to stabilize the charge, right? And what we're going to have is something like this. H2O and OH. Very well. So as you can see, I think it's pretty obvious what we have here is what? Water as a leaving group. So I think everybody knows what is going to happen. These electrons are going to go into and be pushed away towards the water. So what we will have, right, my pen, first I have my pen, there you go, is something like this. Plus water, pretty well. So we are getting closer, right? Because we have a single bond already towards the carbon of the carbonyl group and the oxygen, right? Now we need to create what? Another single bond between this carbon and this other oxygen. How do you think it's going to do that? We already have everything set for that to happen, because again, with another intermolecular reaction, what is going to happen is that these electrons are going to go attack and push the electrons toward the oxygen that, again, it's positive, right? So the reaction should be pretty fast because it's an intermolecular reaction. And the kinetics of the reaction, I'm pretty sure that obey this. Anyway, so what we will have actually is something like this, right? We already have our ketone transformed into an acetal group, so it's an acetone, but it's disguised, right? It's hiding in the form of an acetal group, right? And since we had an acid, that means that we have a conjugated base, any base, it could be a chlorine or something, and that is going to help us to pick up, right, the hydrogen and then return the electrons towards the oxygen. So pretty as that, what we have is the protection group of our ketone plus the conjugated base towards the acid. So we recovered our acid. What we have is our catalyst. So look what we have here. We have the pathway block for a nucleophile to go and attack the carbonyl group. Is not going to happen. Okay, so in the case of the aldehyde, it will be very similar, right? I don't think it's necessary for me to write down the whole reaction mechanism, but if you work like this and you work towards exactly the same conditions and you get something like this, right? With acid, what you will get is something like this, right? And it's very convenient for aldehydes because remember, aldehydes, right, are more reactive than ketones, so we have to take care of them. And this is a very useful reaction that we can use. Very well, so as homework, I'm going to ask you to do this. Think about that you might have this structure, And I want you to tell me how you are going to transform this into this. Give me a moment, I'm counting the carbons here. Excellent. So I'm going to give you some advice. This is what? sp2, and this is what? sp3. And this is what? sp2, and you want to keep it how? As sp2. So from here to here, what you want to do is a reduction. Okay, you can use any source of reductants that you already know. My personal advice would be to use some sort of hydride. Which one? The strong one. Not mild ones. Just go nuts. Okay. So I hope that you find this entertaining and useful, and see you next class. See you later.